And we are live. All right, welcome back, everyone. This is yet another live stream experiment. I definitely appreciate everyone who's bearing with me while I try these different things out. I think that there's a lot of potential for doing live workshops without having to plan it. So I can just log in when I have time, answer some questions, and teach depending on what students need at that time. Right now, April 21st, we are preparing for final exams. A lot of my students are testing in next week or the next month. So I'm going to be doing what is potentially the last free workshop for this semester. That will be tomorrow, Saturday, April 22nd at 8 p.m. Eastern. This workshop is going to cover retrosynthesis practice questions. And in preparation for the workshop, one of my students submitted this in the Study Hall Facebook group. I figured it would be a perfect opportunity to first of all remind you about the workshop, and second of all, to help you realize that just because you see a crazy complex problem on your exam doesn't mean you have to freak out. If you know how to approach a simple problem like this, then, and I say simple because it's a simple approach to complex problems, then all you have to do is run through the questions to help yourself calm down. So you don't need to panic. Just think, what is the approach? And then is there any way to simplify this so that I can answer these questions no matter how scary they look when they show up? The practice problem here is typically taught at the Organic Chemistry 2 level. We are looking at a single starting molecule, which if you can't see it clearly, it's just a 3-carbon chain, and we're looking to create this monstrosity. The instructions specifically say, using propane as your only carbon source, devise a potential scheme to produce 4,4-dimethyl-3-heptanol. Now, as I'm working through this, if you can hear me clearly, if you can see this clearly, just give me a heads up and let me know. I'm keeping an eye on the chat in a separate screen so that I can answer your questions as they come up. The 2 questions that you want to ask yourself when you're looking at any synthesis problem is very, very simple, and these questions are to guide you. The first question is, what is the same? And the second question is, what is different? Once you identify what is the same, you want to see how you can keep that structure in your product. And when you identify what is different, we're looking at anything from the number of carbons in the chain to the functional groups that show up in the chain. And then you can figure out, okay, this is what's the same, I have to keep this. If this is different, I have to change it. How do I create or introduce that difference? So let's start out with the starting molecule. It's just propane. It's a 3-carbon chain. Compared to the product, which is this monstrosity, but specifically I'm looking for what is the same. What can I identify in this product that somehow, some way resembles the starting molecule? Knowing that I'm only starting with propane, I'm going to look for segments of 3 within this molecule. Starting at the top, I see what could be my first propane. Then I see what could be my second propane and my third propane. So this tells me I have 3 starting molecules of propane, and somehow, some way, I find a way to connect them, and then let's see where we're going to go with it. The next thing we want to look for, we identified all the carbons from the reactant to the product. The next thing we want to look for are the functional groups and the location of reactivity. And reactivity means how we're going to connect them. What kind of functional group would I have to put there? Maybe a leaving group, maybe an attacking group, so that I can make that connection. For the first one, we notice that there is an attachment because the rest of the chain is attached at the same carbon that is holding an alcohol. This is a clue that you absolutely have to recognize. If you have an alcohol on your product, it's a secondary alcohol. This means that this right here must have been a Grignard that did the attack on an aldehyde. So let's point out here and say from a Grignard. Now the reactions that I come up with are just what come to mind for me. If you come up with another synthesis opportunity, if you see a different type of reaction sequence, it's not wrong, it's just that this is what happens to come to mind for me right now. Typically, the more complex the reaction, or the more complex the molecule, the more potential pathways you have. So there are many ways to reach your product. This is just my go-to. Grignards are my favorite chain elongation reaction for Orgo 2. If this happened from a Grignard and an aldehyde, that gives me a clue that for the green 3-carbon chain, I want to come up with an aldehyde. I want to find a way to turn it into an aldehyde. This one right here has to be a Grignard to do the attack if the green one gets attacked by a Grignard, so that's something to keep in mind. And then the bottom one, well, if we have a Grignard here, what if we say that prior to being a Grignard, maybe it was an alcohol that then went to an MGBR, MGBR being the Grignard of choice for me. And if I see that as an alcohol given a tertiary before the attack happened, so this portion could have been a tertiary alcohol, that means once again we can go with another Grignard attack saying that this was a carbonyl. So this goes to a Grignard, but initially it could be from a carbonyl being a ketone. That means this one could also be a Grignard. Now there are other ways you can do this reaction, but by thinking of it this way, all we have to do is find out what we can turn into a Grignard, what we can attack into a Grignard, and we are good to go. Let me look at a couple of the questions first in the comments before we continue. Thank you for those of you who say you can hear me. Hey, Pankaj, hope I said that right. Abhishek. For those of you requesting other topics, this is the question that I chose for this session, but I will be doing more live sessions in the future. This link is what I will try to use every time I have a live workshop. So if you're watching this live today, the next workshop is April 22nd, but when I have workshops in the future, I'll have the same link go to the workshop page for that upcoming session, and I try to do 1 to 3 a month depending on how heavy the exams are going on. Question, what's a Grignard? If you don't recognize the name, you haven't learned it. It's one of those scary things that you either recognize it right away or you don't. And if you don't recognize the name, I'm going to wonder if you've covered this yet. So this is specifically covered in a more advanced undergraduate organic chemistry, typically Organic Chemistry 2. Now that we have the steps, I think of this as a roadmap, because you show me this and you tell me how to start reacting. A lot of students will dive into the synthesis right away, but without knowing where I'm going, I tend to get confused, I tend to get lost, I tend to get overwhelmed, and on an exam, you cannot afford those emotions. On an exam, you need confidence. You need to know, this is where I am, this is what I have to do, so let's go ahead and do it. By identifying where every carbon came from, the type of functional group that's going to be required, all I have to do is take it as a roadmap and say, okay, what do I have to do with the green portion? I have to turn it into an aldehyde. What do I have to do with the lower portion? Well, I have to create the whole thing first so that this right here is a ketone, this right here is a Grignard, and then attack it, and then once I have a bigger piece, I can turn that into a Grignard and attack the top. So that means I want to start from the bottom. We'll refer to them by colors so you can see where we're going with it. Let's turn that purple carbon chain into a Grignard. The first reaction we have is to somehow turn this into a molecule that has a Grignard at the end. I'm using MGBR because I like to. You can use MGX. You just tend to have one go-to. It keeps it simple if you know where you're going each time. The question is, how do you do that? And the answer is, I have no idea. Because the starting molecule has nothing on it. And if there's nothing on it, how do I create a functional group? How do I put reactivity on the molecule? We're going to use what I call my favorite reaction, the creating something from nothing. Nothing being a plain carbon chain and something being some sort of leaving group that we can react with. And the way to do that is radical halogenation. If you use something like Br2 with heat or light, and you'll see me write this sometimes as a triangle for heat and this squiggly line for radiation or waves, light waves, that will give me a bromine, but in the more substituted position, because remember, radicals have that stable intermediate very similar to carbocations, where the more substituted radical is more stable. That puts bromine on the central carbon. Problem is, I want it on the end, so I have to do what I call move the reactivity. How do we move the reactivity? Ideally, I want to get a bromine on the end. I don't know how to just move a bromine, but I do know how to do a reaction that will eliminate that bromine and give me a double bond. So for example, if I use a small base like NaOCH3 and add CH3OH, it's its own conjugate solvent, add some heat to favor elimination, Whenever you see something like this, sodium is a positive spectator, get rid of it. OCH3- is negative, it's a strong attacker. I'm envisioning either a substitution or elimination reaction, a 2 type, so SN2 or E2. The solvent is polar protic. That means I'm more likely to get elimination because SN2 would prefer an aprotic solvent. And heat also helps favor elimination over substitution. So everything here points to an E2 reaction. I don't have to worry about stability of the pi bond or which direction or anything because this molecule is symmetrical. So I'm going to put the double bond on this side just so it starts to resemble the product and I can clearly see where I'm going with it. Ultimately, we did this because we wanted to move the bromine, so we have to find a reaction that will now add a bromine to the terminal carbon to the anti-Markovnikov position, because then I can easily turn that into a Grignard by simply reacting with Mg in ether, for example, Et2O diethyl ether. How do I get a bromine in the anti-Markovnikov position? I can react with HBr, but I need peroxides. I need radical conditions. So for example, ROOR is just a generic peroxide, and that will give me the anti-Markovnikov bromine on a primary carbon. This gives me the first piece in the puzzle that I identified from the starting molecule. I wanted this to be a Grignard. I have it. So now let's go ahead and look up to see how we create the second piece so that we can attack. Let's take a quick pause for questions. Thank you so much for nice videos. You are very, very welcome. Rohit says, get married and have kids. Have some kids, don't waste your youth. Rohit, thanks, but no thanks. Clearly you don't understand what we're doing here, so please just log off. Alright guys, let's read a nice comment after that one. Hi Leah, just Google you on YouTube. Okay, let's keep the questions specifically related to this so that we can understand what's going on here. And we are, of course, going to ignore Rohit's questions after that. So I'm not even going to answer your SN1 question. The next thing we want to do is create a ketone out of this, because we said if this is an alcohol that we then turn into a Grignard, we need to have a ketone so that we can attack it with a Grignard. Whenever you have the one starting molecule where you have to do multiple reactions, you don't have to show starting from propane each time. You can take one of the intermediates and simply say I'm going to continue from there. So if I have this molecule already created in the previous step, I can continue from here or I can continue from here. Either option will give me a ketone, so I'm going to show you both in case you forget one or the other on your exam. For the first one, we can simply do an SN2 reaction so that we get an alcohol on the position, the secondary position where the bromine is currently located. To do an SN2 reaction, you eliminate the leaving group and somehow make that your attacking nucleophile. As an OH-, minus will attack and kick it out. If I use something like NaOH, I don't want to use H2O because that is a polar protic solvent. So let's dissolve it in something like DMSO, which is polar aprotic and will guide you towards substitution instead of elimination. That is one simple way to do this, but if you forgot that reaction, for some reason students are not as quick to see this reaction, but this one here is much easier. All I have to do is react with something like H2SO4 in water. That will give me an acid-catalyzed hydration reaction. Acid-catalyzed hydration will simply break the pi bond and ultimately give me an OH in the Markovnikov position. Both of these reactions gave me an alcohol, so all I have to do is oxidize that alcohol using any number of oxidizing reagents that you should have memorized, like KMNO4, Na2Cr2O7, one of those reagents that have a whole lot of O for oxidation. And I showed a O in brackets just to remind you oxidation, whatever you learned in class, because a lot of professors prefer a specific one. That will give me the ketone. Now I want to take these two together and see what our next step is. We simply want an attack. So let's see what happens when we react these two together. We'll bring them onto the next page. Did we turn that into a Grignard? Yes, just to remind you, we turned it into a Grignard into the last step. That's the one we want to use. So let's see what happens if we have this molecule with an MgBr, reacting it with the ketone. that will just have a standard Grignard attack. Kick that up, that's step 1. Step 2, you want to add some water. Some professors will want you to show as H3O+. Some will just say H2O because it's a mild acid. Regardless, make sure you don't put it together. You need that step 1 and step 2 because if you put the water in first, you're going to destroy the Grignard and stop your reaction. What does that give me? Let's draw it the way that our product is written. So we'll have the 3-carbon chain with the purple coming right under it. So the blue, our 3-carbon chain, is like this. Attached, we have the new bond, and then we have the purple group under it. When we attack the Grignard, the ketone now becomes an O-, which in the next step becomes an OH. That's an alcohol. Let's go back again to our starting molecule using the guide that we already predicted. So we're not going through reaction after reaction and thinking, oh man, what do I do next? What do I do next? Instead, we already have it outlined. It's so much easier to outline first and then go through step by step. We predicted that after we have an OH, we need to turn that into a Grignard. That's very easy. We've already shown how to do that. In this case, because it's a tertiary alcohol, we don't want to do an SN2 type reaction to get a bromine on there. Instead, we want to go SN1. Tertiary carbocation will be very, very stable. So all we do is react this with H3O, not H3O+, I'm sorry, we want an acid, but we ultimately want something like a bromine on there. So if we react it with HBr, H+ is ultimately the bribe to make OH into OH2+. Good leaving group, break away, carbocation intermediate, Br- will then swoop in and attack. And that will give me something that looks like this with a bromine, and of course the rest of the chain hasn't changed. So that's sitting right here. And then we want to take this and turn it into a Grignard. So once again, Mg, something like diethyl ether or other ether. Swap out that bromine for the Mg in its place with a Br. We have our Grignard. Let's go back now to see the final step that we need. The final step is one more propane, but this time we have an alcohol in the end that we predicted came from an aldehyde. So we need a 3-carbon aldehyde starting from here. Or do I have to start from there? Or can I simply say, what if we take something we have already done? So that is one option. The other option is to take this and actually put a primary alcohol. So let me show you both. Again, our goal is an aldehyde. So if we had a bromine at the end, like this, how would we turn that into an aldehyde? I don't know, but I do know how to turn it into an alcohol, which I can then turn into an aldehyde. Let me take a moment first to... Alright, there we go. I apologize, guys, for this person writing very, very rude comments. I just figured out how to block them, so we did that. If anybody got offended, just ignore them. People find that when you're on the internet and you can't see people face to face, then I guess they just take their own personal vendetta and try to throw it out on other people. So if you were offended, don't even worry about this. So let me take a few moments to look at the other comments. Danielle, yes, I can read your comment. Stella, thank you very much. I see a question on why are radicals like carbocations. So I'm going to direct you to, I have a carbocation tutorial where I think I mentioned radicals. I can't think of it off the top of my head, but if you go to my website, go to layer4sci.com, and then in the search type carbocation stability, or just do a Google search for layer4sci and carbocation stability, that's going to come up. Question, can you explain how I got the alkene? Go review your E2 reactions. I have an entire series on substitution elimination, so a lot of what I did here with the SN1, SN2, E1, E2 is in that series. Make sure that you go ahead and review that. Alright, so back to synthesis. Thank you, Mohammed. I appreciate it. Yes, we are here to just learn about organic chemistry. And if you guys see any other rude comments, I don't know if there's a way to flag it, but if you can flag it, that will help. And guys, just ignore it, right? Some people just, I don't know, maybe he was having fun. I don't know. Alright, so here we are. We are trying to turn this bromine into an aldehyde. And the first type of reaction we're going to do is simply SN2 again. What did we use last time? NaOH, because we need that alcohol intermediate. Put it into something that is polar aprotic to avoid elimination. I think we used DMSO before, so let's go ahead and do that again. That will give me an SN2 reaction. The bromine is going to be replaced by an OH, so now we have an alcohol. And this is where you have to be careful with your oxidation. The typical oxidizing reagent is going to give you an oxidation that goes all the way. So in a secondary alcohol, there's only the option for a ketone unless you start going extreme, meaning breaking the carbon chain. But with a primary alcohol, you typically go to a carboxylic acid, which we're not looking for here. We're looking for an aldehyde. So instead we're going to use PCC. PCC, pyridinium chlorochromate, is a milder oxidizing reagent that with a primary alcohol will stop halfway through at the aldehyde. And the way I remember it is that PCC starts with a P. It's kind of like a prude. It doesn't go all the way to a carboxylic acid. Instead, it only goes partway to an aldehyde. A fun tip for you, when you're trying to remember things, the funnier, the weirder, or the dirtier the mnemonic, the more likely you're going to remember it. So I challenge you to try this one. And just for other things, give yourself funny ways to remember. That's one way to get the aldehyde. But I said there was another way that you can do it. We had an intermediate with an alkene. If you take this alkene and you go for an anti-Markovnikov alcohol addition, so this is something that I teach in the alkene reaction series, you'll see something like this: BH3, THF, NaOH, H2O2. This is your standard hydroboration for the B. That'll give you an alcohol at the primary position. And once again, we can use PCC to give us the aldehyde, which is what we were looking for. So if you weren't sure which one to start with, either one gives you what we need. Let's go back to the starting molecule. And we needed an aldehyde. We have the aldehyde, so now let's see how to put all of it together. We left off with this molecule as a Grignard. So let's see what happens when we take our aldehyde. I'll redraw it just so we're kind of on the same line here. So we'll take our aldehyde, which we just created. We'll react it with that big complex Grignard we created in the last step. So let's move this down, showing that my reagent is the Grignard in step 1, step 2, H3O plus or H2O, depending on which one your professor uses. That will protonate the alcohol that I form. And this will give me a final product. I wanted to show you exactly how it all lines up. So this is what we had. The attack happened right here. So this Grignard attacks, kicks out one of the bonds, the pi bond, so that will show right here. We have the green 3-carbon chain exactly as we see it, but now we had an O-, which then got protonated to an alcohol, and that is our final product. Let me show you that it matches up exactly to what we predicted. Going back to the beginning, right there. So you see that we had our 3 starting propanes. That's carbon 1, 2, 3. The second one, 1, 2, 3. And the third one, 1, 2, 3. In summary, what we did here, because you're not going to see this exact problem on your exam, but rather you want to see the thought process, right? Because if you memorize this, what I just showed you here, if you don't see this again, how are you going to pass your exam? But if you think about the steps that we took, the thought process to get each answer, you'll have a much, much better foundation for going into your exam. We're going to focus on this concept specifically of how to approach retrosynthesis in the upcoming workshop. It's tomorrow at 8 p.m. Eastern, tomorrow, April 22nd. If you're seeing this video down the line, the link that I'll use for live workshops is leahforsyth.com/workshop, and it'll just give you information on the next one if there's something planned. But to review what we did today, we started with the 2 questions. What is the same and what is different? We're comparing anything and everything from the reactant to the product. So the same in terms of the number of carbons, how many. In this case, we had 3 carbons, but we found 3 different pieces of that 3-carbon chain. What is different is the fact that they're connected to each other, the fact that we have functional groups, and just then trying to find the patterns. How can I create that difference? So we looked at this molecule and we said, An OH appeared, but there's a connection. Anytime you see an OH with a new carbon attached, you want to think Grignard and carbonyl. In the first one, it was an aldehyde. In the second one, we said if this was a Grignard, what if prior to that it was an alcohol, which came from another Grignard attack, and that's how we figured out what to do here. So all we did was turn this into a Grignard. Once we had a roadmap of where we were going to go and exactly how we were going to connect each of the individual pieces, we didn't have to guess, okay, I did this reaction, what next, what next? I simply kept going back to my initial notes, and the initial notes told me I needed to start here, turn that into a Grignard. I need to turn that into a ketone. I need to attach these two. Then I need to turn this into a Grignard. I need to turn this into an aldehyde, and the whole thing just fell into place by following those steps. If you have any questions on this, write it in the chat. If you're watching this later, just leave a comment on the video. I do get a lot of comments, so I don't always respond to them, but I will try, especially before finals. So let's take a quick look at any of the comments that are here right now. Does this become a video after it's over? Yes, I'm going to be posting this on the channel as soon as I'm done. It takes a few minutes to process and buffer. Daniel, thank you. A question, we cannot use an amine acid instead of OH. I'm not sure I understand what you mean by amine acid. NaOH is a base, so we're specifically looking for a base or a nucleophile. So NaOH can actually be a base or a nucleophile, and depending on the situation, we create the conditions to make sure that it does what we want it to do. Abu, you are very welcome. Question, we know actually alcoholic NaOH gives elimination of HBr. I'm not sure where you're going with that, but if you're referring to what I did over here, this is just one way to carry it out. There are many other methods you can use to carry out this reaction, and it doesn't even have to be bromine. It could be chlorine, it could be iodine, whatever it requires, whatever you require to make a Grignard would work in this situation. This just happens to be what I am focused on. Question, please make a workshop on retrosynthesis. That's exactly what tomorrow's workshop is going to be about. Make some amine videos. I have so many video ideas and so little time. This is one of the reasons I'm really excited about YouTube Live, because I don't have to plan out the recording and then sit down and do the recording and the editing and the transcription. I would literally just set up my computer and started recording. So here we are, and the video will be up as soon as we're done. I will definitely be playing around with YouTube Live a lot more because it's so much easier than making a video. Question, it would be nice if you saved the note file. So this is just a question that came up from the Facebook group. So the Organic Chemistry Study Hall has a Facebook group where you can post questions. One of the students posted a question that I felt I wanted to explain, and instead of typing it out, I recorded the video. So I do maybe not videos as in-depth as this, but I do a lot of videos in the study hall and a lot of answers and explanations. So if they ask for the notes, I'll be happy to send it to them. But if you're interested in the study hall, it's an entire month is way less than what I charge for a single hour of tutoring, and the link to sign up is layforpsi.com/join. All the details are there. You can cancel anytime. So if you want the notes, if you want more videos, I'm definitely going to point you to the study hall, because that is the focus of where I provide all the Orgo tutoring for my students. Quick question. Okay, guys, if you're typing questions that are not related to what we did today, let's hold off on that. I'm specifically just looking for questions on this, and I don't see any more questions. So thank you everyone for tuning in on a very random Friday afternoon. Hopefully this helped you not just in the specific reactions we did, but also in the thought process of how to take a potentially overwhelming question and just simplify it to the point where it makes sense, so that you know what to do, you know how to think, and hopefully get through it faster with more confidence. And just knowing that you know what to do, I think, is so important for your exams. Hope to see everyone on the live workshop. If you're seeing this before April 22nd, it's going to be at 8 p.m. Eastern. If you're seeing this in the future, the link layforpsi.com/workshop will redirect to the live workshop if I have another one planned. If not, it'll just redirect you randomly to my website. But keep trying that link every week, because I do a workshop 1 to 3 times a month depending on how heavy the finals are for that month. Fewer in the summer, more around now, more in November, so it depends on the time of year. All right, everyone, enjoy. Take care.